The national grid is what gets electricity from the power station to your home or building. They vary slightly from country to country, but broadly all work in the same way. We'll start at the power station, where the electricity is generated. In essence, the power station converts other forms of energy, like fossil fuels or the wind, into electrical energy in the form of an electrical current. Using fossil fuels as an example, this is how the generator in the power plant works. The fuel, for example coal or natural gas, is burned to convert the chemical energy within it into thermal or heat energy. This heat is used to boil water to turn it into very high pressure steam. The steam is then led to a turbine, which starts to spin at very high speeds due to the force of the steam acting on the blades of the turbine. This converts the thermal energy of the steam into the mechanical or kinetic energy of the spinning turbine. The turbine is connected to the electricity generator and converts that mechanical energy into electricity using the principle of electromagnetic induction. Inside the generator are coils of wire and magnets. Very loosely, electricity is generated here when there is a relative motion between the two. More specifically, when the magnetic flux through a conductor changes, an electromotive force, EMF, and therefore a current, is induced. Magnetic flux is the amount of magnetic field passing through a particular surface or area. So, in our case, the amount passing through the coil of wire, this amount changes with the relative motion between the coil and the magnets. This creates an EMF, which you can think of as the pump for the electricity to flow. Just as a pump may be used to bring the water up to a fountain for it to flow out, the EMF gives the boost needed for the current to flow. It's vital to reiterate that, for an EMF to be induced, there has to be a change in magnetic flux. Simply having a constant flux won't generate an EMF. So, either the coils could spin while the magnet stays still, or vice versa, where the magnet turns instead, using the rotational energy provided by the turbine. For efficiency's sake, modern generators use turning electromagnets and stationary coils, as they require fewer complex and bulky parts and allow for more precise control of the voltage output. The electricity produced is now ready to be distributed throughout the country. But before the electricity is sent off into the power lines you see all across your country, its voltage must be increased. This is because the power lost in transmission is proportional to the current flowing through it squared, and so for the same power, an increase in voltage reduces the current, making the transmission more efficient. A step-up transformer is used to do this. A transformer is a machine that changes the voltage of a circuit, either by increasing it or decreasing it. It contains a primary and secondary coil around either side of a core made of a ferrous metal, usually silicon steel. An alternating current, a current which changes direction many times a second, passes through the primary coil. The current induces a magnetic field around the primary coil and the core, which, due to its properties, keeps the field confined within the space taken up by the core, including through the secondary coil. Since the current is alternating, the magnetic field induced around the core changes direction many times a second, so the magnetic flux present on the secondary coil is also constantly changing. This induces an EMF across the secondary coil, and current flows through it. This is just like in the generator, but instead of physical motion creating the changing magnetic flux, it is instead produced by the alternating current. Now here's the key point. The induced EMF across a coil is directly proportional to the number of turns it has, and in a step-up transformer, the secondary coil contains more turns than the primary. In other words, the ratio between the number of turns in the two coils is equal to the ratio of the EMFs across the two coils. Because, of course, the changing magnetic flux would create an EMF across the primary coil as well. So, the secondary coil would have a larger induced EMF, and therefore a larger voltage than the primary, and consequently it would have a lower current, the outcome we needed. The electricity now travels over vast distances across the country, made possible with the great network of large pylons and overhead lines that you see scattered all around. It eventually reaches more local and regional stations, where its voltage is reduced using step-down transformers. In these transformers, the secondary coil has fewer turns than the primary, and therefore, for the same power output, a lower voltage and higher current is induced. The voltage needs to be reduced so that it can safely be used for everyday purposes in the home. The stepped-up voltages would simply be too high and dangerous. Systems of smaller pylons and lines then carry the electricity to the places it's needed, allowing homes and other buildings to fulfill their everyday and commercial needs.